Welcome you all to the afternoon session of this lecture series by Professor Sylvain Ervedoza. So Sylvain, you can go ahead.
Well, thank you. So welcome everyone. Hello. I hope that you did not forget everything I said last week, but let me start by recalling the result of last time. Okay, so we have here the following Carleman estimate. So we have omega, a smooth bounded domain of RD. Small omega is an open subset of capital omega, which is strictly included in capital omega. We have phi, a weight function, which is assumed to have some smoothness. So here I have put C4 just to be on the safe side, but C2 is enough. And on this weight function, I have several assumptions. So the first one is that the infimum of the gradient is strictly positive outside small omega, which means somehow that outside small omega you can, sorry, there is an update of my pad coming into play, so I hope it will not disturb the process, but okay. So we have this condition of that gradient of phi does not vanish, which means that the level sets of phi are a foliation of the domain outside small omega. We also have a second condition, which is possibly more difficult to understand, which is this one involving beta, which, as I said last time, in fact, it's related to the curvature of the level sets compared to the convexity in the direction of the weight function. Okay, so really here, this is convexity. Well, this one is curvature of the level set. Okay, and then finally there's a condition on the boundary, but okay. This one is only to say, well, to simplify a little bit the computation, to say that the boundary is a level set of phi, and that you have the normal trace, which is negative, which means that somehow that the weight function is at its maximum inside small omega. Okay, and then you have this Carleman estimate here, where again you have to realize that the constant here is independent on S. Okay, so another way to say it is to express that we know explicitly how the constant in these Carleman estimates depend on S. Okay, so here remember we have the operator which comes here. Okay, so here we consider the Laplace operator. And here we have an observation term. So this one is localized.
Sylvain?
Yes?
Can you just adjust the sound because we are not able to hear properly?
I'm very sorry about that. Is it better now?
Okay. Okay. You can just stop a little bit because you can check and then just wait for 1 minute or 2 minutes. Just check the sound.
Okay, so I'm speaking just to say that the weather is nice here, so I hope it's the same in India. So everything's fine for the conference?
Yes, it is fine here, but you are able to hear us properly?
Yes, it's very good. For me, it's very good. And for you?
No, for we are not able to hear you properly.
But
it's
I'm
low,
speaking
voice
more
is
or less
low.
the same as last week. So I don't know, maybe I can close some app on my
We are trying to increase in the volume from our side.
Okay.
You can wait for 2 minutes, maybe he is actually increasing the sound.
Okay, good.
So can you talk now so that we can check?
Yes, so maybe I could continue. I mean, anyway, this was only reminders of what I've been telling last week.
Yes, now I think it's okay.
It's okay?
Yes.
Okay, very good. So again, we had this strict pseudo-convexity condition. So as I told you, this is related to foliation of the domain, okay, and curvature. And of course, we cover what we did during the first lecture on a weight function depending only on x1. Okay, so now I'm going to prove it. So I think we are the 20, okay, lecture 3. We are 20, February 20. Okay, so I will try to give two results, which are in fact, I believe, interesting regarding this Carleman estimate. So the first one is the proof. Okay, and for the proof, I will do that in a slightly simplified context with stronger assumptions. Okay, and so namely, I will assume that there exist coefficients alpha and beta strictly positive such that the infimum of the gradient of phi over x is larger than alpha. So still this condition of non-criticality of phi in omega minus omega bar. And I will also assume that the infimum of Laplacian phi times psi square plus 2 d2 phi of psi xi. So this is, again, d2 phi is the Hessian matrix, right? Applied to psi xi. This is larger than beta for psi of modulus 1 and x in omega minus omega bar. Okay, so this is, of course, a stronger set of assumptions. Okay, but we will see that, in fact, in 1D, well, for the Laplace operator, well, we can do that without restricting the geometry. So let me assume that and prove the Carleman estimate. So to prove the Carleman estimate, as usual, I will work on a conjugate variable. Okay, v equals to exponential s phi of u. So we had Laplacian u equal to f in omega with u equal to 0 on the boundary. And of course, this translates as Laplacian of v exponential minus s phi equals to f. And since we do not like to have weight only on one side, we will really look on the conjugate operator. So we will set capital F equal to exponential s phi times small f, so that this is f exponential minus s phi, with v on the boundary equals to 0, and this yields the system Laplacian of v minus 2s gradient of phi gradient of v plus s squared gradient phi square v minus s Laplacian phi v equal to capital F in omega, with v on the boundary equals to 0. So, okay, I do not want to detail the computation. It's only computation, nothing more. Okay? So here we are. And what I will do to get the Carleman estimate directly. So meaning I will not perform this Fourier transform in the transverse coordinate and so on. So to get the Carleman estimate directly, what you can do is simply write that f square is Laplacian v minus 2s gradient of phi gradient v plus s square gradient phi square v minus s Laplacian phi v in L2, and then develop. And do the computation. So this is more or less the idea. Well, in fact, it's slightly more involved than that. So what we will do to develop is to separate the self-adjoint part and the skew-adjoint part. Okay, so let me define the operator P1 of V equals to Laplacian V plus S square gradient of phi square V. So this is self-adjoint part. And there's also a skew-adjoint part, which I will call P2, which is minus 2s gradient of phi gradient of V minus S Laplacian phi V. And in fact, in this, you see S has to be thought as a derivative. Okay, so like this one is of order 2, this one is of order 2, this one is of order 2, but this one is of order 1. So in fact, on the one of order 1, we can do whatever we want, right? So when I'm saying this is in order 2, so Laplacian is 2 derivative in space, right? So this is order 2. And then you see S squared, so S squared is of order 2. For the first term in P2V, you see you have S gradient of V. So S is like 1, gradient of V is like 1. So at the end, you got 2. Okay? But the last one, it looks like it is of order 1. So in fact, you can do pretty much whatever you want with this term. So what you will do, what is convenient for the computation, is to put a 2 in here. And then to introduce some reminder. So this is more or less the skew-adjoint part. And we have a reminder, RV, which is minus S Laplacian phi V. And then we have that P1. So that F plus RV equals to P1V plus P2V. Okay, and then we say that the norm of P1V plus P2V square equals to the norm of F plus RV square. So these are L2 norms on omega. So this one, of course, this is less than the norm of F square L2, well, with a factor 2, plus 2 times RV in L2 of omega square. And you see this one, in fact, it is bounded. So I recall that RV is minus S Laplacian of phi times V. So this one, in fact, this is bounded by a constant times S squared times V L2 of omega square. And if you believe in the result, you should get an estimate on S3 norm of V L2 square. So it means that this is really lower order term. Right? So on this one, really, this is a reminder and you don't care. For the rest here, what you write is that it is P1V square plus P2V square plus, of course, some cross product, 2P1V, P2V in omega. Okay? And the hope is that the cross product will be mainly positive. And this is that will give the Carleman estimate. Okay, so just to understand this strategy, so imagine, well, it's very convenient to consider this in terms of operators or in symbols. So you think in symbols. So I don't know how familiar you are with symbols. So usually you have to deal with more regularity in space and so on to be on the safe side. So you simply, so P1 is the operator which corresponds to minus Laplacian, sorry, plus Laplacian plus S square gradient of phi square. So the symbol would be P1 of X psi equal to minus psi square plus S square gradient of phi X square. And so if you put at a scale H equal to 1 over S, this S square would be like 1 over H square. And then you should have something like that, right? So this is what you have for P1, and for P2 you have minus 2S gradient of phi gradient, minus S Laplacian phi V, I think with a 2. So the symbol would be 2S gradient of phi minus I psi, right? So this is gradient phi of X. So when you look at the symbols, so if you put it as an H, the H will vanish in here. No, sorry, the H will be, sorry. We'll have H psi here. Okay, and the last term is lower order term. So in the principal symbol, it has no impact. Okay, and then you see somehow the computation that you are doing is simply computing P1 plus P2. So here I've put P2, okay. So you are doing that, right? P1 plus P2 of V, L2 square. This is P1V plus P2V plus the cross product. And the cross product, you see it's P1V, P2V plus P2V, P1V. And of course, one is Q-adjoint and the other one is self-adjoint, right? So it means that this guy here should be P1. Sorry. I think there's the wrong sign somewhere, but okay, I don't know why. So it's P2, no, it's P1, P2 minus P2, P1 of V times V, right? So it means that the symbol in here should be P1 square plus P2 square plus the symbol of the commutator. And of course, the commutator comes, well, the symbol of the commutator, sorry, which is 1 over I of P1, P2. Okay? And so what you want basically is that this guy has to be strictly positive. So I'm only giving the idea. So here it's a bit rough. Okay, so that it is strictly positive. In fact, I should say elliptic. Okay, as an operator in S psi. And this is precisely the Hermander's condition is the following. The Hermander condition is if P1 equals to 0 and P2 equals to 0, then this one is strictly positive. Okay, so it's another way to formulate it. I think that one of you asked the question last time, okay, about this subellipticity condition, right, in terms of symbol. And of course, it's the same as the one I wrote. It's only a computation, so you can realize, for instance, when you look at the symbols of P1, that in fact the critical part is when the modulus of H psi equals to the modulus of gradient of phi, and when H psi is orthogonal to gradient of phi. Okay, so which is precisely the set of conditions you have in here, right? So gradient of phi and psi have the same size and they are orthogonal. It's exactly the same. Okay. So, but then I still have to do the computation here just to check that it works by doing computation. So let me go back to the computations of P1, P2V. So let me just keep this one. So I want to compute the integral of P1V, P2V. So I will call it the sum of Ig for I equal to 1 to 2, and the sum for G equal to 1 to 2, where Ig is the cross product of the if term of P1 times the G term of P2. Okay, so let's do that. It's Iy1 is Laplacian V times minus 2s gradient of phi gradient of V. So this is minus, okay, 2s Laplacian V gradient of phi gradient of V. So you do one integration by part. You have 2s gradient of V gradient of phi gradient of V. And there's a boundary term. On the boundary, since I have Dirichlet boundary condition, everything is normal. So this is dnv times dn phi dnv. So this is dnv square. Okay, since v on the boundary equals to 0. And then, okay, let me just write it. So what is this thing is the sum of div, di of dgv, dg5, dgv. This is the sum of the ig. So this is d2 phi of gradient v, gradient of v. plus the sum of dg phi, so this is gradient of phi, gradient of v square over 2. And so, of course, on this one, I will also do an integration by parts, so that I11 would be 2s d2 phi gradient of v minus s Laplacian phi gradient of v square. So the two cancels. There is also one additional term coming on the boundary from the integration by parts, comes with a 1, so it should, at the end, you should have this. dn v square dn phi. Then we have I12, which is the integral over Laplacian, over omega of Laplacian v times minus 2s Laplacian phi v. This is minus 2s, which is 2s integral over omega of Laplacian phi gradient of v square minus 2s that comes over plus, it's gradient of v, gradient of Laplacian phi minus v. Of course, I write it as gradient of v square over 2. And at the end of my computation, I should have this term first, and then minus s of d2 phi v square. Okay, I21. So I21 is the integral of S2 gradient of phi square V times minus 2s gradient of phi gradient of V, and this is minus S3 gradient of phi square gradient of phi times gradient of V square. So you do one integration by part, and you get that it is S3 divergence of gradient of phi square gradient of phi V square. For I22, this is the integral over omega of S square gradient of phi square V times minus 2s Laplacian phi V, and of course you have nothing to do. This is minus 2s3 integral over omega of gradient of phi square Laplacian phi V square. Okay, so if you put everything together, you get that the integral of P1V, P2V is, okay, the big thing. So you have to track first, well, there are many ways to do that, but you have to keep all the terms. So first I will simply look at the terms in gradient of V squared. So I have this one here, this one, and that's it, right? So you see here you have minus s Laplacian phi gradient of V squared, and here it comes over 2, right? So what you have at the end is 2s d2 phi gradient of V plus s Laplacian of phi gradient of V squared. Okay, so this is for the terms involving gradient of V. Then you have a term coming from the boundary. You have only one, okay, which is minus s dn phi dn V squared. Okay, so this one has been put. And then what remains is the term in V to the 3, in V squared, sorry. And there you have S3 divergence of gradient phi squared gradient of phi minus 2 S3 gradient of phi squared Laplacian phi plus I think I'm missing one. So this one I've been put. This one, okay, and it remains this one, minus S Laplacian phi squared. Okay, so what about this? So here, we'll use that dn phi is negative. So this term here, for all this term here, it is positive. Okay. The terms in gradient of v squared. So I should go back to the assumption. So on the assumption, I have this thing here. Of course, this is homogeneous in psi. Okay, and so you can apply it to psi equals to. So sorry, I think there's missing something. No, it's good. So you can apply it to psi equals to gradient of phi. Equals to gradient of v. And then all this thing here is in fact larger than beta as gradient of v squared. Okay, so this is the assumption. For the other one here, I just realized that I forgot an assumption again. So here there is an additional one. I'm sorry, I forgot about it. It's minus gradient of phi squared Laplacian phi plus 2d2 phi gradient of phi is larger than beta gradient of phi squared. And this is precisely the one you need to handle the terms in v squared. So let me go here. Basically, with this assumption, you are able to say that it is larger than s to the 3 v squared times gradient of phi squared minus constant s v squared. Okay, and then you know that gradient of phi squared, this is bounded from below by alpha, so at least on omega minus omega bar. So then, if you want it on sorry, this is on omega minus omega bar, right? So if you want it on omega, well, you just have to remove. So this one is on omega, but you have to remove another one here on small omega. Okay, and in fact, I'm a bit, sorry, I'm a bit messy today. So here, I've used an estimate which is valid only on omega minus omega bar, okay? So on this guy here, I have an estimate on omega minus omega bar, okay, the estimate from below. And if it is if you are in omega, the only thing you can say is that it is bounded by constant times s to the 3. Okay. So, okay, I'm sorry, I've been a bit messy here. For this one, it's the same thing, right? In fact, in omega, the only thing you can say is that it is bounded like this. And so what you get at the end is S3 alpha square V square plus S beta square gradient of V square is bounded. So this is on omega, is bounded by the two. I think the 2 has been cancelled anyway, so as the norm of f in L2 of omega square plus constant S square V square plus constant S3 plus S, I'm sorry. This is on omega plus constant S on omega V square plus constant S3 on small omega V square okay, and the constant does not depend on S. Okay, so then you simply take S log. It will allow us to absorb the lower order term on the right by the terms you have on the left. So it's alpha square. Okay, and you get there exists a constant C positive such that for all S larger than S0, so there exists S0 large enough, okay, such that S3 V squared plus S gradient of V squared is less than a constant times the norm of F L2 square. So these ones are on capital omega, and the other one are on small omega. So this is S3 V square plus S gradient of V square. Okay, so that basically ends the proof. There are still some details to do, so we can remove the observation S gradient V square by some kind of Chowdhury inequality. So basically you want to say that it is bounded by this. Provided here you take omega 1, which is slightly larger. So this is, okay, for okay, so this is a classical stuff. So you just take a cutoff and then you realize that V somehow satisfies the Laplace operator, okay, with some lower order terms. But since it is a Laplace operator, you can get estimates simply by multiplying it by V, okay? And if you introduce a cutoff, you multiply it by chi V, where chi is a cutoff, then you will manage to get this. And once you have that, you are done. Okay. So I'm sorry, I've been a bit messy, but the story here is that under some conditions on the weight function, you have a Carleman estimate. So these conditions, if you want to understand it properly, probably you need to go to semi-classical analysis, where your Carleman parameter that I call S should be considered as 1 over h in the semi-classical setting. This is very efficient inside the domain. On the boundary, it requires some technical difficulties and some proper definitions of the semi-classical operators there. And sometimes it's not required when you have, for instance, Dirichlet boundary condition where everything can be done very easily simply by integration by parts. And somehow also integration by parts is more flexible in terms of regularity of the data and so on and so forth. So well, basically, I think it's good to know the both proofs and to be able to use them both. Okay. What's next? So next, I'd like to comment on the assumptions on the weight function. So basically, we had two sets of assumptions. So we had, sorry, these ones here. Okay. Well, we had another set of assumptions, which was, in fact, the true one. Okay, so here what is missing is that for all x. Oh, sorry, base one is here and the other one is back. Okay, so I'm claiming that the first one is stronger than the other. So let me just explain it. Is that clear? Well, in fact, it is clear that the second one implies the first one because you can simply put Laplacian phi in the second estimate and see what happens, right? So I will just consider the first set of assumptions. The first set of assumptions. So for the first set of assumption, I will prove the following. Let omega, capital omega, be smooth bounded domains. D, omega, well, non-empty, of course. Maybe I should say it. And omega strictly included in capital omega, then there exists a function phi which satisfy all the assumptions. And for the proof, in fact, it starts with the following remark, that there exists a function psi such that psi on the boundary is omega, of the boundary is 0, psi is positive in omega, and the infimum, so this is the step, the first step, of gradient of psi is strictly positive. Okay, so how to prove that? So I will mainly sketch it. If you want to see the proof in a very precise and pedagogical manner, you can go to the book by Tuxnack and Weiss in the last, I think it's Appendix C. So, and it starts with the following result, which is more or less classical, but okay, if you want to see the proof, you can go to Tuxnack and Weiss, is that there exists a function psi 0 such that psi 0 on the boundary equals to 0, psi 0 is strictly positive in omega, and psi 0 has only a finite number of critical points. So in fact, this property, this is generic in the sense of Bell, so there are many functions like this. Okay, so this is the starting point. So I believe that Marius Tuxnack is maybe still in Bangalore with you. So if you have questions about this construction, I mean, you can go to him. Okay, so once you have this, to construct psi, you do the following thing. So you do some surgery. So basically you have your domain, omega. And for psi 0, you have some critical points. These are the critical points. Of psi 0. And then you have your set small omega. And what you want is to have a function psi which has no critical points outside small omega. So what you are going to do is to say, okay, we have some critical points here. And each of these critical points, we will connect it to small omega. You can always do that. It's a nomotopic argument. Okay. So once you have that, around each of these paths, you will construct some kind of neighborhood of the path, okay, a small neighborhood, a tubular neighborhood of your path, such that they do not intersect each other, right? So it can be very small. So you have this kind of tubular neighborhood. You have many, okay? And then on this tubular neighborhood, you will change psi naught by leading the critical points from here to the domain. So, okay, so you have surgery inside each of these neighborhoods. So it's not very difficult, in fact, to see how it works. So you can imagine that it is like a mountain, right? So the critical points are the tops of your mountain. So you have all your summits. Okay, you have a finite number of summits, and you want to put all the summits into small omega. Okay, so basically what you do is simply you take your summit and you steer it inside your domain small omega, and then you have shifted your critical point inside small omega. So that's all you are seeing. So at the end of the process, you will have a psi, which is 0 on the boundary, strictly positive in omega, and such that the infimum of gradient of psi in omega minus omega bar is strictly positive. Okay. So what is the second step? The second step is what is called the convexification argument. So remember, I've told you that there are two conditions. In fact, the first condition is to get the foliation, okay? So this was done in step A. In step A, we have constructed a psi such that the level set of psi do a foliation of the domain omega minus small omega bar, okay? But then you have this kind of competition between the convexification in the direction of the weight function and the level sets. Okay, so what you want to do is to look for phi under the form phi equal to f of psi for f sufficiently convex. Okay, so in order to do that, well, there are many ways to do this. So for f sufficiently convex compared to, sorry, I should say compared to the curvatures of the level set of psi. Okay, so the typical choice is to take f of s, no, sorry, f of x equals to exponential lambda x for lambda large enough. Okay, and then you see, of course, f second is lambda square of f of x, right? So it's very convenient because you can compare the second order derivative and so on, and you get, each time you get powers of lambda. So when you do the computation, you will have phi equal to exponential lambda psi. So you'll have that the gradient of phi would be lambda gradient of psi times phi. So you'll get that Laplacian of phi is the divergence of gradient of phi. So it means that it is lambda square gradient of psi squared times phi plus lambda Laplacian psi phi, and d2 phi against psi will be lambda square gradient of psi dot psi plus lambda d2 psi psi. And so here you see you have different order of magnitude. So here you have lambda square. And of course, these are the terms that will be dominant. Okay, so these are dominant terms. As lambda goes to infinity, right? So sorry, here's, I think the square is missing. Okay, and then it's only a matter of computation. Lambda large enough. So in fact, as soon as you have the geometric inside, it is clear that this is what is needed, right, to construct sufficiently convex, pseudo-convex weight function. Okay, so as soon as you have your foliation, it will simply convex in the direction of the gradient, which is what it does. Okay, so just to finish the result today, I want to give one application to unit continuation. It's a theorem. So we take Q in L infinity of omega. We take a vector field V in L infinity of omega the power D. So omega here is a smooth bounded domain of RD. Okay, we take omega strictly included in omega. Then if you in H2 intersected H10 satisfies Laplacian U plus QU plus W gradient of U equal to 0 in omega. So U, it is in H10, so of course it satisfies this. And U vanishes in a non-empty open set so maybe I do not need small omega. So then U is identically 0. And so for the proof, we do, well, as before, so we have the Carleman estimate. With observation in small omega and the appropriate weight function. And then you'll get that there exists C such that for all S larger than 1, the norm of S to the 3 U exponential S phi L2 square plus S gradient of U exponential S phi L2 square. It is bounded by a constant times Laplacian U exponential S phi L2 square plus constant S3 U exponential phi L2 of small omega. So this one vanishes. right? So then you just have to bound the terms in Laplacian U, and recall that Laplacian U is minus QU minus W gradient of U. So it will be less than a constant times the norm of Q at infinity of omega squared times U exponential S phi plus the norm of W at infinity square times gradient U exponential S phi L2 square. So for S larger so for S3 larger than the norm of Q at infinity square and S larger in regarding larger than the norm of W at infinity square, we'll get so we can absorb the right hand side terms by the left hand side term, and we get U vanishes ever. Okay. So here you see that the scales, so some comments. So the scale is S larger than the norm of Q L infinity 2/3 plus the norm of W L infinity squared, right? So this is the scales that comes out of this Carleman estimate. If you, what time is it? Well, so probably it's time to stop. So I just want to say that it can be adapted to potentials Q and W, which are in LP class. But if you want to reach the optimal LP class, you will need to go to LP Carleman estimates, which exist, but whose proofs are quite different than the ones I showed today. Well, thank you.
So thank you, Sylvain, for the wonderful talk. So now I ask the audience if they have a question, they can ask. Also in the online mode, if there is a question, they can ask Sylvain.
Yeah, thank you very much for a nice talk. So my question is, for a general conjugated elliptic operator, how to choose P1 and P2, that symmetric and squisymmetric operator?
Well, they are given, in fact. You do not choose them. They are. So let me go back here. Oh, sorry, can you say it again, your question? Maybe I'm missing the point.
So if you consider the general operator, let's say general elliptic operator.
Yes.
Or let's say higher order operators, let's say biharmonic operator. Okay.
Okay.
So how to choose this P1 and P2? Because in that case, there will be so many terms involving phi, right?
Yes, but still the symbols are quite clear, right? So if you want to give insights on the choice of P1 and P2, probably the best way to do that is by using symbols. Okay, so for instance, you have a very nice introductory article by Gilles Lebeau and Jérôme Rousseau. I think it's about 2010, but I never know the date, which is a survey on Carleman estimates, which presents everything in terms of symbols. So you can try to go there and see what comes out.
Okay, thank you, sir. I have another question. So what is the advantage of convexification? In this case, we are convexifying this weight, right?
Yes.
So what is the advantage in this setting? I mean,
so I think this is related to something I've been telling last time, if I'm not mistaken. So in here, probably I said, you see when you have phi, which depends only on x1. Okay, here it is. Okay, so you take something which is not convex, you will see that the cost of the quantification of unique continuation, for instance, is not the same. So this is the not convex case, right? So this is the one you obtain with the linear weight, and this is the one you obtain with a strictly convex weight function, like x1 squared plus x1, something like that.
so basically,
Okay.
I mean,
So you see,
just by using convexification, you can add the lower order terms, right?
yes. So this is for the lower order terms with respect. So this is the zero order term. If you go to the one order term, if you do not convexify, you will need it to be small to absorb it, right? Because so I should go back even before. So you see here, this is k to the power 0 here. So if you want to absorb a term like w gradient of u, you will need w to be small. Okay? Are you still here?
Yeah. Thank you very much.
So really the powers of k, or the powers of your Carleman parameters, are an information about can absorb or not. Okay, and so for instance, if you do cutoffs arguments, in the cutoffs you will have gradient terms, right? So you need to have good estimates in the gradient as well, with the positive powers of your Carleman parameter. Otherwise, you will not be able to localize. Okay.
So Sylvain, in chat box, there is a online mode, there is a question. So if you can see, or I will read.
Yeah, I can see it, but you can read it, I mean, for the ones who are not have their computer on. So let me go back to this point.
So to absorb the gradient term in the last step of Carleman's proof, I think omega 1 should be in omega to be able to absorb the V term.
No, omega 1 should be larger. Well, I don't know. Well, so the proof is really you multiply, let me write it here. So I will do that really on Laplacian u equal to f. You should do it on v, but it doesn't change a lot. So you just multiply by a cutoff times u, where chi equals to 1 in omega, and chi is compactly supported in omega 1. So when you do that, you see you'll have k chi u Laplacian of u. It is minus chi of gradient of u squared. And then if you do two integration by part, probably you will have something like that. Laplacian chi over 2 and u squared. Okay? And of course, this guy is localized. Oh, sorry. This guy gives you informations. This is where chi equals to 1. And to absorb this term here, you should realize that the Laplacian of chi will be localized in omega 1. Okay, and that's it. Basically, that's it. Okay, so certainly omega should be smaller than omega 1. Is that okay? Does it answer your question, Ed Group?
Please, on the right hand side of the last inequality, you have S3 integral on omega 1.
Yes.
This term, how to absorb it?
I do not want to absorb it. I mean, this is here. Right?
So the control region or the observability region is omega 1?
Yes, so if you do that, indeed, you need to enlarge a little bit the observation set. That's true. But
Because
these are open sets. So in fact, you don't really care. I mean, you can call a small omega in the beginning, a slightly smaller set, and then enlarge it a little.
So this term is still remaining there, yeah?
It is still what?
It will be not absorbed.
No, it will be the observation. So this one, it's not absorbed.
Guidance. Okay, thank you.
Yes. So yes, in the case of boundary observation, you can get a Carleman estimate for an arbitrary small observation set. So basically the proof is the same. So I had to do some choices. So I didn't want to speak about localized observation on the boundary, but it is exactly the same. So you will need, so if you are observing on the boundary, it means that in your Carleman estimate, you will need the conditions in the whole set capital omega. And on the boundary, you will only need the condition phi vanishes and dn phi negative on the part on which you do not observe. And then you do exactly the same. At least when you have Dirichlet boundary condition. Does it answer your question, Alex, Inda? Yes? Good. That's all for today, I think.
Hello. So I had one simple question, which is that the curvature beta, it shows up only in front of the gradient term, right? In the estimate, just before we pass to the constants. Which means if I take a flat weight, I get the same estimate, but without the gradient absorbing term, right? If the curvature beta,
yes,
only shows up in front of the gradient, right? So just before you pass to the last weight. So if I took the curvature beta to be 0, I do not get a gradient, which means I can recover what you had done earlier. And then after that, it's just an energy estimate to get the gradient, right? So is that how you recover the linear weight from this?
Indeed, you can do that. So in fact, this is when you take beta equals to 0, this is related to the framework of limiting Carleman weights, which is something which have been developed in the context of inverse problem, probably around 2008 or 2009. There's a work, so probably I will forget some authors. I think it's Gunther Ullmann with Carlos Koenig and Johannes Sjöstrand, I believe, about limiting Carleman weights. And this is more or less what they do. In fact, what they do is is a little bit different in the sense that they take a convexified version of the limiting weight, and then they pass to the limit in the convexification. Okay, so you see I have a convexification argument, f of psi. So if you take psi, or phi, which saturates the second condition, then you can take phi plus epsilon phi squared. Okay, and then this guy will be slightly more convexified, and so it will satisfy everything with lower term here, beta, which would depend on epsilon. And if you are able to track it down very precisely, then you will manage to get a Carleman estimate at the end by passing to the limit epsilon goes to 0.
Okay, thank you.
Okay, if there is no other questions, so let us thank Sylvain again. And